Welcome to the Deep Dive. Today we're really getting into something fascinating, but also, let's be honest, often a source of frustration in AI. It's this challenge. You train these brilliant machine learning models, but then getting them to actually work nicely across different tools, different frameworks, different hardware, that's tough.
Oh, absolutely. It's a surprisingly tricky problem, and it can seriously slow down getting cool AI stuff out into the world.
Yeah.
Imagine, like, you've built this amazing engine, but it only fits into one very specific proprietary car chassis. That's kind of what it was like for a lot of AI models.
Right.
Developers burning hours, days, weeks, just trying to translate a model from, say, a research setting into something that can actually run in production.
Exactly. So our mission today is to really unpack Open Neural Network Exchange, or ONNX. Think of it almost like a universal translator, but for AI models. A bridge built to connect all those, separate islands. We're going to dig into why it even needed to be created, how it actually works its magic, and most importantly, how it helps AI move from that cutting-edge lab research phase to actually being deployed in the real world, no matter what system it needs to run on.
Yeah, and you're going to get a handle on how ONNX tackles what some people have called the interoperability crisis in AI. It's a big term, but it was a real problem. We'll break down its main parts, show you how it can give you a serious performance boost, and how it lets models run pretty much anywhere. We're talking cloud servers, tiny little edge devices, even, believe it or not, right inside your web browser.
Wow.
Get ready for some, hopefully, aha moments about where AI deployment is heading, getting your models to speak that universal language.
Okay, let's get into it. To really understand why ONNX became so important, we need to paint a picture of that interoperability crisis. So, think about the AI development scene just a few years back. You had these incredibly powerful frameworks, but they were kind of, well, specialized.
Very specialized.
On one side, maybe a research team is using PyTorch. It's got dynamic graphs, it's super flexible, great for trying new ideas, pushing the boundaries.
Right, perfect for research agility.
Yeah.
But then maybe the deployment team, they're all set up with TensorFlow. TensorFlow's got this robust, production-focused ecosystem, great for scaling things up reliably.
Both amazing tools, no doubt.
Phenomenal tools.
Yeah.
But that very specialization, while good for certain tasks, created this huge headache. Framework lock-in.
You called them walled gardens earlier, and that's a perfect description. They were like these separate ecosystems. A model trained beautifully in PyTorch. You couldn't just, pick it up and drop it into a C++ production environment that was expecting a TensorFlow saved model, or run it easily on mobile phone.
Nope.
For an MLOps engineer listening right now, what was the day-to-day pain you saw most often before ONNX really took hold? Can you make that frustration real for us?
Oh, it was just pure inefficiency, honestly. I saw teams spending weeks, sometimes even months, basically rewriting models from scratch in a different framework just to get them deployed.
Wow, rewriting.
Yeah, you'd have a brilliant data scientist crafting something amazing in PyTorch, and then a totally separate engineering team, essentially duplicating all that logic in TensorFlow or C++.
That sounds incredibly wasteful.
It was. Duplicated effort, wasted time and money, introduced all sorts of potential for new bugs during the translation. It just created these massive bottlenecks, getting innovation out. Just moving a model between teams or platforms or different hardware became this whole separate, often dreaded engineering project.
So the need for, what did you call it, model maneuverability?
Yeah, model maneuverability, portability, basically the ability to move models around easily. That need became super, super clear.
Okay, so the stage is set. The pain is real. How did we start tearing down those walls? And this is where ONNX steps onto the scene, right, as this Rosetta Stone for models.
Exactly. It came about as a joint effort, initially between Facebook and Microsoft back in September 2017.
And fun fact, I read it was originally called Toffee.
That's right. It started as an internal project name, Toffee, within the PyTorch team, before they launched it publicly as ONNX, this collaborative open source thing.
Oh, and it caught on quick.
Yeah, pretty fast. You saw major players like IBM, Intel, AMD, NVIDIA all getting involved relatively early on. They saw the need to.
So what's the magic? How does ONNX actually do this universal translation? It's not just waving a wand, presumably.
No, definitely not magic. It works by defining an open, standardized format. Critically, it's designed with compiler optimization in mind from the get-go. It gives us a way to describe the model as a computation graph, specifies a common set of built-in operators. Think of these as the vocabulary, the basic building blocks like convolution or matrix multiply and standardized data types. All this creates what's called an intermediate representation, or IR. It's a standardized blueprint so precise that any tool that understands ONNX can pick it up, understand it, and run it. And often, because it's designed for optimization, run it even faster than the original framework might have.
So it's more than just making things compatible, it actually changes the whole workflow.
Fundamentally,
Yeah.
it decouples the training environment from the deployment environment. That's the key phrase, decoupling.
Right.
You can train your model in PyTorch, TensorFlow, scikit-learn, whatever you like best for the job. Then you export it to this standard .ONNX format. And then a completely different team, using a different runtime, can load and execute that .ONNX file without needing to know or care about how it was originally trained.
That sounds liberating for developers. Choose the right tool for each stage.
Exactly. Research in one tool, deploy using a standard pipeline.
And what about its future? Is it controlled by one company?
Good question. To ensure its long-term health and community-driven evolution, ONNX became a graduate project within the Linux Foundation AI back in November 2019.
Ah, the Linux Foundation. So that means it's governed by community consensus, not just Microsoft or Facebook dictating things.
Precisely. It gives it stability and ensures it evolves based on what the whole industry needs, which is really important for an open standard like this.
Okay, so ONNX is this universal language, this Rosetta Stone. But just knowing the language isn't enough, right? You need dictionaries, translators, maybe even libraries of pre-written texts.
Great analogy.
And that's where the ONNX ecosystem comes in. It's definitely more than just that .ONNX file format. We can think about it in maybe 4 main parts, like the blueprint, the engine, the translators, and the library.
That's a perfect way to break it down.
Yeah.
So the ONNX format itself, the .ONNX file, that's your blueprint.
Yeah.
It's the open standard specification for representing the model as that computational graph, defining the operators, data types, the whole structure.
Got it. Blueprint, then the engine.
That's the ONNX runtime, usually called ORT. This is a high-performance inference engine. Its job is to take that ONNX blueprint and actually run it, execute the model, and do it really fast across all sorts of different platforms and hardware accelerators.
Okay, engine makes sense. And the translators?
Those are the converters. These are the absolutely essential tools that bridge the gap. Things like TF2 ONNX for TensorFlow models or Scale2 ONNX for scikit-learn models. They take a model trained in its original native framework and convert it into that standard ONNX blueprint format.
Right, translating from the native language to the universal ONNX language and the library.
That's the ONNX Model Zoo. It's basically a curated collection of popular pre-trained state-of-the-art models that are already in the ONNX format.
Oh, cool.
Yeah, so you can just grab them off the shelf and use them directly in your ONNX compatible application, saving you the training or conversion step for common models.
So for the MLOps engineers listening, the benefits here go way beyond just, oh, now my PyTorch model can run in a TensorFlow environment. It's deeper than that.
Much deeper. Yes, interoperability is the big headline, the reason it was created. But ONNX has profound impacts on actual performance, your development speed, and the sheer flexibility you have in deploying models.
Let's unpack that framework flexibility a bit more. It's not just avoiding rewrites, it's about enabling better workflows, right?
Absolutely. Think about it. A data science team can iterate super fast, try really cutting-edge stuff using PyTorch's flexibility. Once they have a great model, they just export it to ONNX. Then the deployment team, maybe focused on C++ or Java, can take that exact same ONNX file and plug it into their standardized, potentially highly optimized ONNX runtime pipeline. They don't need to become PyTorch experts.
So everyone uses the best tool for their part of the job. That sounds way more efficient.
Exactly. And this standardization unlocks something really powerful: shared optimization and hardware access. This is where it gets really interesting, I think. Because there's this single defined ONNX standard, hardware vendors, NVIDIA with their GPUs, Intel with their CPUs and accelerators, ARM for mobile and edge, they can pour their optimization efforts into making ONNX operations run incredibly fast on their specific silicon.
Ah, so they optimize for ONNX, not for every single framework individually.
Precisely. When NVIDIA builds a super fast Fuse kernel for a common sequence of ONNX ops on their GPUs, any model converted to ONNX, whether it started in PyTorch, TensorFlow, JIGAX, whatever, can automatically benefit from that optimization just by running through ONNX runtime on that NVIDIA hardware.
Wow, okay. That kind of democratizes high performance, doesn't it? The model's origin becomes less important than the standard itself.
Exactly. It democratizes access to specialized hardware acceleration.
Yeah.
Your model gets faster not because you rewrote it for CUD, but because it speaks the standard language, ONNX, that the hardware vendor optimized for.
Which logically leads to reduced time to market, less rewriting, less friction.
It is faster deployment. You cut out those huge chunks of time spent just translating models between frameworks. It streamlines that whole path from research code to a production-ready asset. It takes a massive amount of friction out of the MLOps cycle.
It really does sound like a game changer. So to see how it achieves this, let maybe peek under the hood a bit more. Deconstruct the actual ONNX format. You said it's a structured data format.
Yeah, at its heart, an ONNX model file .onnx is structured data serialized using something called protocol buffers, or protobuf.
Protobuf, I've heard of that. Google developed it, right?
That's the one. It's widely used, very efficient for encoding structured data compactly. And crucially, it's language agnostic, which is why you can easily load and parse an ONNX model in Python, C++, C, or C#, JavaScript. The protobuf definition handles the cross-language compatibility.
Okay, so it's built on a solid foundation, and structurally, how is it organized? Is it layered?
It is. It's hierarchical. At the very top level, you have the model proto.
Yeah.
Think of this as the main container for the whole model. It holds the actual computation graph, but also essential metadata, like the opset version, which is super important. We'll come back to that, and maybe info about how the model was produced, the producer name.
Okay, model proto is the wrapper. What's inside?
Inside that is the real meat, the graph proto. This defines the model's logic as a directed acyclic graph. A DAG.
A DAG, right. Like a flowchart with no loops going backwards.
Exactly. The graph proto contains lists of the graph's inputs, where data comes in, and outputs, where results come out. It also has a list of nodes, which are the individual calculation steps, and importantly, initializers.
Initializers. Are those the weights?
Usually, yes. The initializers typically store the pre-trained weights and biases of the neural network as constant tensors within the graph itself.
Got it. And each step in the graph, each calculation is one of those nodes.
Right. Each node proto represents a single operation. It'll have an optype, like conv for convolution or matmul for matrix multiplication. And crucially, each node specifies its inputs and outputs using string names. These names act like pointers, connecting the output tensor of one node to the input tensor of the next node, defining how data flows through the graph.
Okay, so the nodes define the operations and the names link them together. What about the data itself that's flowing?
That's defined by TensorProto and ValueInfoProto. ValueInfoProto describes the shape and type of the data flowing along an edge, its name, its data type, like float32 or int8, and its dimensions. TensorProto, on the other hand, is used to store the actual raw numerical data, primarily for those constant tensors like weights stored in the initializers.
We've dissected the .onx file now, and you mentioned something earlier about the graph proto being static. Why is that important? It sounds almost limiting.
But that static nature, that seeming rigidity, is actually a deliberate design choice. And it's arguably ONNX's superpower when it comes to performance.
That's so.
Because the graph is static and fully defined up front, an execution engine like ONNX Runtime can perform incredibly powerful whole graph analysis and optimizations before a single calculation happens.
Okay. It can see the entire plan beforehand.
Exactly. It's like a logistics expert optimizing an entire factory assembly line layout before production starts. Because ORT knows the full sequence of operations, the data types, the shapes, it can do things like operator fusion, combine multiple simple operations like convex normalization, real U activation, into a single, highly optimized fused kernel. This drastically reduces function call overhead and improves memory locality.
I see. Fewer steps, faster execution.
Right. It can also do constant folding, pre-calculating parts of the graph that only depend on fixed weights. It can eliminate redundant nodes. It can even partition the graph intelligently to run different parts on different hardware accelerators, like setting some ops to the GPU and others to the CPU.
You just can't do that level of upfront optimization with a dynamic graph that changes as it runs, can you?
Not nearly as easily or effectively. That static graph is key to unlocking peak performance in deployment.
And the vocabulary used in that graph, the optype in each node, comes from a standard list.
Yes, ONNX defines a comprehensive set of standard operators. Everything from basic math, add, mul, to core ML building blocks, conv, matmul, maxpool, and even more complex things needed for various model types.
Now, you mentioned opset version was critical. Let's circle back to that. What is it, and why does it matter so much?
Okay, this is a really crucial concept, and honestly, it's probably the most common source of friction or errors when people start working with ONNX.
Good to know.
Think of the opset version like a version number for the ONNX operator specification itself. As AI evolves, new operators get added, maybe for new types of layers, or sometimes the behavior of existing operators needs refinement. Each .NX model file explicitly declares which opset version it was created for and adheres to. This version number guarantees the exact set of operators available and their precise mathematical definitions.
So it's like saying, this model was built using the dictionary from year 18.
Exactly. And here's the rub. The ONNX runtime version you use for deployment also supports operators up to a certain opset version. If you try to load a model exported with, say, opset version 18, but your ONNX runtime is a bit older and only understands operators up to opset 17,
It's going to fail.
it's going to fail to load the model. It'll complain about unknown operators or incompatible definitions.
Yeah.
Compatibility between the model's opset and the runtime supported opset is absolutely essential.
Okay, so tip number 1, always check your opset versions match between export and deployment.
Definitely. Saves a lot of headaches.
Now, these ONNX graphs sound complex, especially if you didn't build the model yourself. Maybe you downloaded it from the model zoo. How do you even visualize or debug what's inside that .onNX file?
Yeah, looking at the raw protobuf definition isn't very intuitive. Thankfully, there's an absolutely indispensable tool for this called Netron.
Netron.
N-E-T-R-O. It's become the de facto standard visualizer for ONNX models, and frankly, for many other neural network formats too. It's a standalone app, works offline, and it's brilliant.
So what does it let you do?
It's super easy. You just open your .onNX file in Netron. Immediately shows you a clean, interactive diagram of the computation graph.
Oh, nice.
You can zoom in, pan around. In a side panel, you see the crucial model properties right away.
Yeah.
Producer name, producer version, and that all-important opset version.
Good.
Then you can click on any node in the graph. Netron highlights it and shows you all its details. The op type, any specific attributes it has, like kernel size for a convolution, and critically, the names of its input and output tensors.
So you can trace the data flow visually, see what connects to what.
Exactly. You can follow the connections, see where the weights initializers feed in, understand the overall structure. It's invaluable for sanity checking a converted model, debugging issues, or just getting familiar with a model someone else built. Honestly, I can't imagine working with ONNX without Netron.
Sounds essential. Now, mostly people will probably use those converter tools like torch.onnx.export, right? But is it possible to actually build or change an ONNX model directly, like programmatically?
It is, yes. While converters handle maybe 95% of use cases, sometimes you need finer control. Maybe you want to perform some really specific graph optimization or to graph surgery, swapping out parts of a model, or even build a model entirely from scratch directly in the ONNX format.
Okay, for the power users, how do you do that?
Well, the classic way is using the ONNX.helper module in the official Python ONNX library. This gives you a fairly low-level API where you essentially construct the graph proto, node proto, etc., piece by piece, mirroring the protobuf structure. It's powerful, but can be quite verbose.
A bit tedious, maybe.
It can be. But the ecosystem is improving here, too. There are newer tools emerging. For instance, ONNX Modifier allows for some visual editing of graphs. And perhaps more interestingly, there's a library called ONNX Script. This aims to let you define ONNX functions using much more natural, idiomatic Python syntax. Like you could write a Python function def add ab.return plus b decorated appropriately, and ONNX Script translates that into the corresponding ONNX graph nodes. It makes programmatic authoring feel much more like regular Python coding.
Okay, that sounds promising for more advanced customization. So we've got the blueprint, the .onNX file. We've talked about visualizing it, converting to it, even building it. But the blueprint doesn't do anything on its own. We need that engine. ONNX runtime, ORT. Let's dive deeper into that. What makes ORT tick?
Right. ORT is where the rubber meets the road. It's the high-performance engine that actually executes your ONNX model. Developed in open source by Microsoft, it's designed for speed and cross-platform compatibility.
And it's used in real products.
Oh, yeah, heavily. It powers inferencing in huge Microsoft services. Think Bing search ranking, features in Office, various Azure AI services. It's battle-tested at massive scale.
And you mentioned performance gains earlier.
They consistently report significant gains. Even just on CPU, they often see an average speedup of around 2x compared to running the model in its original framework, thanks to those graph optimizations we discussed.
Wow, 2x on CPU alone is impressive. And it works across languages.
Yep. The core is C++ for performance, but it has official APIs for Python, C#, Java, JavaScript, making it easy to integrate into different application stacks.
That cross-platform aspect is huge. But the really interesting part seemed to be how it handles different hardware, like GPUs, TPUs, etc. You mentioned execution providers, or EPs.
Exactly. The execution provider framework is ORT's secret sauce for hardware acceleration. Think of EPs as pluggable backends or drivers within ONNX Runtime. Each EP is specialized for a particular hardware target.
So there's like a CEDO EP for NVIDIA GPUs, maybe one for Intel's OpenVINO.
Precisely. There's a CD execution provider, a Tensort execution provider, which leverages NVIDIA's Tensort library for even more aggressive GPU optimization, an OpenVINO execution provider for Intel CPUs and integrated GPUs, a Quorum execution provider for Ample hardware, QNN execution provider for Qualcomm chips on mobile devices. The list keeps growing.
Okay, so how does ORT use these EPs when I give it my ONNX model? Does it just pick one?
It's smarter than that. It uses a process called graph partitioning. When you load a model and tell ORT which EPs you'd like to use, you give it a prioritized list. ORT does the following. 1. It analyzes the entire ONNX graph. Okay. 2. It queries each EP in your priority list asking, can you efficiently run this specific node or this subgraph? 3. Based on the EP's capabilities, ORT intelligently partitions the graph, assigning chunks of nodes to the most specialized EP available that can handle them.
So it might run a part of the model on the GPU via the CUDA EP and maybe another part on the CPU.
Exactly. And this is critical. Any nodes that aren't claimed by one of your specialized EPs, maybe the GPU doesn't support a specific exotic operation, automatically fall back to the default CPU execution provider.
Oh, that's clever. So it doesn't just fail if the GPU can't do everything.
Right. You get best effort acceleration. It uses the specialized hardware where it can, but the model still runs correctly thanks to the CPU fallback. This provides incredible robustness for production. You maximize performance without sacrificing the ability to actually run the model. It's a huge advantage over systems that might just crash if a single operation isn't hardware accelerated.
That sounds incredibly practical. Okay, let's make this concrete. How would I actually run inference using ORT in Python? Walk me through the basic steps.
Sure. It's pretty straightforward. 1. Installation. You pip install on X runtime for the CPU version, or pip install on X runtime GPU if you have an NVIDIA GPU and the CDA toolkit setup.
Right.
2. Load model and specify EPs. You create an inference session, you give it the path to your .onNets model file. Crucially, you also provide a list of strings specifying the EPs you want to use in order of preference. For example, CO execution provider, CPE execution provider.
So try CD first, then CPU as fallback.
Exactly. 3. Prepare inputs. You need to figure out what inputs your model expects. Metron helps here. Then you format your input data, usually as NumPy arrays, making sure the data type and shape match the model's requirements. You put these into a Python dictionary where the keys are the model's input names, strings, and the values are the NumPy arrays.
Okay, a dictionary mapping input names to data.
Yep, let's call that input feed. 4. Run inference. You call session.run. You typically pass none as the first argument to get all outputs, and then your input feed dictionary. This executes the model. 5. Get results. The sesh.run call returns a list of NumPy arrays representing the model's outputs in the order defined in the ONNX graph.
Seems logical. Install, load with EPs, prepare inputs, run, get outputs. What about that I/O binding thing you mentioned for GPUs? When would I use that?
Right, I/O binding. This is more advanced but super important for performance-sensitive GPU applications, especially things like real-time video processing. The issue is, normally, even if your data starts on the GPU, maybe from another library like PyTorch running on CUA, the standard session.run involves copying that data to the CPU, feeding it into ORT, which then might copy it back to the GPU for the CUB EP, running inference, getting results back on the CPU, and then maybe you copy them back to the GPU again. Lots of copies.
Yeah, that sounds inefficient.
Very. I/O binding provides an alternative API that allows for zero-copy data transfer. You can essentially tell ORT, my input data is already on the GPU at this memory address, and please put the output data directly onto the GPU at this memory address.
So you bind device memory directly to the model's inputs and outputs.
Exactly. It avoids those costly round trips between CPU and GPU memory, which can give you a significant performance boost, especially if your pre-processing or post-processing also happens on the GPU. You keep everything on the device.
Got it. Okay, that covers running inference. Now let's shift back to the developer's core workflow. Getting the model into ONNX in the first place and then making it run as fast as possible, conversion and optimization.
Right. The first step is almost always conversion from your training framework.
Let's start with PyTorch since it's so popular. How does that work?
PyTorch has excellent built-in support via the torch.onnx.export function. It works by tracing. You provide your PyTorch model, a sample or dummy input tensor with the correct shape and type, and the path where you want to save the .onx file.
Tracing. So it runs the model once with the dummy input and records what operations happen.
It's exactly. It executes the model's forward pass and records the sequence of PyTorch operations, then translates those into the corresponding ONNX operators. Key parameters you need to set are opset version. You must specify this. Pick the latest stable one supported by your target ORT version, input names and output names. Give clear string names to your model's inputs and outputs. Essential for feeding data correctly later. Dynamic axis. This is important. If you want your model to handle, say, variable batch sizes or images of different heights widths at inference time, you use this to tell the exporter which axes are dynamic.
Okay, export seems straightforward enough, but you stressed verification earlier. How crucial is that step?
Absolutely non-negotiable. Conversion isn't always perfect, especially with complex models. You must verify. Step 1. Use ONNX.checker.check model on your exported file. This performs a basic sanity check on the ONNX graph structure itself.
Okay, syntax check.
Step 2, and this is the critical one. Perform a numerical check. Run the same input data through your original PyTorch model and through the exported ONNX model using ONNX Runtime. Then compare the output tensors using something like numpy.testing.assertclose.
Assertclose. So checking if the numbers are basically identical within a small tolerance.
Exactly. This confirms that the conversion process didn't subtly change the model's mathematical behavior. Skipping this step is asking for trouble down the line. Silent accuracy drops are the worst kind of bug.
Got it. Verify syntax, verify numbers. What about TensorFlow? How do you convert from TF?
For TensorFlow, the main tool is a separate library, TensorFlow on NX, often used via its TF2ONNX command line tool or Python API. The most common and generally most reliable input format for TF2ONNX is TensorFlow's saved model format, which packages the graph and weights together.
Similar process. Convert, then verify.
Yep, same principle. Convert your saved model using TF2ONNX, specifying the target opset, then run on NX.checker.check model, and absolutely crucially, perform that numerical comparison between the original TensorFlow model's output and the ONNX runtime output for the same input. Verification is just as vital here.
Okay, makes sense. Now, conversions aren't always smooth sailing, are they? What are some common roadblocks people hit? You mentioned control flow earlier.
Yeah, control flow is a classic one. Remember, ONNX graphs are static. Python code often uses dynamic control flow, like standard ifelse statements based on tensor values during the forward pass.
Right.
When torch.onnx.export traces the model, it might only trace one path of that ifelse, leading to an incorrect or incomplete graph. This is called a graph break.
So how do you fix that? You can't have if statements.
You need to use control flow operators that are part of the ONNX standard and understood by the tracing mechanism. PyTorch, for example, now provides operators like torch.cond, which represent conditional execution within the computation graph itself, rather than relying on Python-level ifs. You often need to refactor your model code slightly to use these graph-aware control flow ops for successful export.
Okay, use the framework's graph-compatible control flow. What about custom operators? What if my model uses some special layer or operation that just doesn't exist in the standard ONNX opset?
That's another common hurdle for more cutting-edge or specialized models. If your framework uses an operation that has no direct equivalent in the target ONNX opset, the standard converters will likely fail.
So, dead end.
Not necessarily, but it gets significantly more complex. The advanced solution involves defining a custom ONNX operator for your special operation. You basically invent a new op type within a custom domain. But just defining it in the ONNX graph isn't enough. You then also need to implement the corresponding kernel for that custom operator within ONNX runtime itself, essentially. You have to teach ORT how to actually execute your new custom op, potentially writing C++ code and integrating it with ORT's build system.
Wow, okay, that sounds like a serious undertaking.
It is. It's usually reserved for situations where that custom op is absolutely essential, and the performance benefits justify the significant engineering effort involved. For most people, trying to stick to standard ONNX ops is the way to go.
Good advice. Okay, so we've converted our model, verified it, dealt with any tricky bits. Now we want to make it fast. Let's talk optimization. ONNX Runtime has built-in optimizers.
It does, and they're very powerful. ORT can perform various graph optimizations automatically when you load the model, or you can apply them offline and save the optimized model.
What kinds of optimizations are we talking about?
They range from simple to quite complex. Basic optimizations include things like constant folding. If part of the graph only depends on constant inputs, like weights, ORT can pre-calculate that part and replace it with the result. Redundant node elimination. It can remove nodes that don't actually do anything during inference, like identity operations or dropout layers, which are only needed during training.
Makes sense, cleaning up the graph. What about more advanced stuff?
That's where extended optimizations come in, and the most impactful one is usually operator fusion.
We touched on this, combining nodes.
Exactly. ORT can identify common sequences of operations like a convolution layer followed immediately by batch normalization, followed by a ReLU activation, a very common pattern in CNNs. Instead of executing 3 separate operations with overhead for each, it can fuse them into a single, highly optimized kernel that performs all 3 steps much more efficiently, reducing memory bandwidth usage and computation time.
How do I turn these on?
When you create your inference session in ORT, you can set session options. One key option is graph optimization level. You can set it to enable basic or extended optimizations. ORT applies them when it loads the graph. You can also use ORT tools offline to apply these optimizations and save the resulting optimized.onx file.
Okay, graph optimization seems like a clear win. Then there's quantization. This sounds a bit more involved. Reducing precision.
Yeah, quantization is a really powerful technique. Feels almost like black magic sometimes. The basic idea is to reduce the numerical precision used for the model's weights and sometimes the activations flowing through the graph. Typically, you go from standard 32-bit floating point numbers, FP32, down to 8-bit integers, INT8.
Why would you do that? Doesn't that lose information?
It does lose some precision, but often the impact on the model's final accuracy is surprisingly small, especially for deep learning models, which tend to be fairly robust to this, and the benefits can be huge.
Like what?
1. Model size. INT8 uses 4x less memory than FP32, so your model file size can shrink by up to 75%, huge for edge devices or faster downloads. 2. Memory bandwidth. Less data means less memory needs to be moved around, which is often bottleneck. 3. Faster compute. Many modern CPUs, and especially specialized hardware, GPUs and NPUs, have dedicated highly optimized INT8 compute units that are significantly faster than their FP32 counterparts, so inference latency can drop dramatically.
Okay, smaller, faster, potential accuracy hit. Are there different ways to do quantization? You mentioned static versus dynamic.
Right. ONNX Runtime supports a couple of main approaches. Dynamic quantization. This is simpler. It quantizes the weights offline, but the activations, the data flowing through the graph, are quantized dynamically on the fly during inference. It's easier to implement, requires no calibration data, and is often effective for models like RNNs and transformers where activations can have wide dynamic ranges. Performance gains are decent. Static quantization. This usually gives the best performance. Here, you quantize the weights offline, and you pre-calculate the quantization parameters, scale and 0 point, for the activations as well. This requires a calibration step where you run a representative sample of your typical input data through the model to collect statistics about the activation ranges.
So static needs extra data, but it's potentially faster.
Exactly. Because the activation quantization parameters are fixed up front, the inference calculations can be purely integer-based, which is often much faster, especially on hardware with native INT8 support. It's generally the preferred method for CNNs.
Okay, let's put all this together. A kind of capstone project idea. Say we want to deploy a real-time object detection model like YOLOv8. How would we use ONNX optimization and deployment strategies for different scenarios?
Great example. This really highlights how the target deployment drives your choices. Phase 1, model sourcing and conversion. First, you get your YOLOv8 model. The Ultralytics library actually has a handy export function. You'd export YOLOv8, a smaller variant, to ONNX. Key thing. Remember to set dynamic, true during export, because object detection often needs to handle varying input image sizes or batch sizes.
Okay, get the ONNX file, make sure it's dynamic.
Phase 2, optimization and benchmarking. Now, the crucial comparison. You create and benchmark 3 versions. 1, the original FP32.ONNX model. 2, an FP32 optimized.ONNX model after applying ORT's graph optimizations like Fusion. 3, an inte-quantized.ONNX model using static quantization. Since YOLO is a CNN, static is usually best. You'd need a small calibration dataset for this.
And you'd measure latency, maybe throughput, and model size for each.
Precisely. Let's imagine some results. Maybe the original FP32 takes 125 meters per inference. The graph-optimized FP32 drops to 98 meters, a nice 1.3x speed up. But the static INT8 quantized version, maybe it plummets to 45 meters, a 2.8K speed up over original, and the model size shrinks from, say, 13 METLB down to 3.5 METLB.
That's dramatic. That benchmark data really tells a story.
It absolutely does. And that data directly informs Phase 3, deployment, which becomes a choose-your-own-adventure based on where you need the model to run.
Okay, adventure path A.
Path A, the cloud API with fast API. Here, your main constraint might be throughput and scalability, less so model size or absolute minimum latency. You'd probably choose the FP32 optimized model. It's faster than the original, but avoids any potential accuracy risk from quantization.
Makes sense.
You'd wrap this model in a fast API web service. Load the ORT session on startup for efficiency. Write Python functions for pre-processing. resizing, normalizing the input image, and post-processing, interpreting the model outputs, non-max suppression for bounding boxes. Create an endpoint that accepts an image upload, runs inference, returns the detected objects, then containerize the whole thing with Docker and deploy it to your favorite cloud platform.
Standard cloud deployment, leveraging ONNX for performance and framework independence. Okay, path B.
Path B, the edge device with Raspberry Pi. Now, constraints are totally different. You're running on low-power hardware, limited memory, limited compute. Real-time performance is key.
So that INT8 model is looking pretty good now.
Absolutely essential. Here, quantization isn't just an optimization, it's an enabling technology.
Right.
The in-quantized model is the obvious choice due to its small size and significantly faster inference. Your deployment involves setting up the Pi, installing the ARM version of ONNX Runtime, probably using OpenCV to grab frames from a connected camera. Your Python script runs in a loop. Capture frame, pre-process, run inference using the INT8 or RT session, post-process the detections, draw bounding boxes on the frame using OpenCV, and display the result. You're aiming for real-time object detection directly on the device.
Cool. And path C, something different again.
Path C, the browser with ONNX Runtime Web. This is super interesting. The goal here is to run the entire inference client side in the user's web browser. No backend server needed for the AI part.
Wait, run YOLO in the browser? How?
Using ONNX Runtime Web, it's a version of ORT compiled to WebAssembly, WASM for CPU execution, and it can also leverage WebGL or the newer WebGPU standard for GPU acceleration directly in the browser.
Wow.
Again, that small, fast, and quantized model is likely the best choice to minimize download size and run quickly on potentially less powerful client machines.
Benefits here are privacy. Data never leaves the browser, and zero server-side compute costs for inference.
Exactly. The setup involves some basic HTML for an image input and a canvas to display results. Then, JavaScript code. 1. Include the ONNX Runtime Web Library, maybe from a CDN or NPM. 2. Load the INT8 ONNX model. 3. When the user selects an image, use the HTML Canvas API to get the pixel data. 4. Pre-process the data and create an ORT. Tensor, the ORT web equivalent of a NumPy array. 5. Run the inference using session.run. 6. Post-process the results in JavaScript and draw the bounding boxes on the canvas.
That's incredible. The same optimized ONNX model deployed across cloud, edge, and browser. That really shows the flexibility.
It really does. This whole journey, from understanding the why of the interoperability problem to the how of conversion optimization like quantization and these diverse deployment paths, that's the power of the ONNX ecosystem.
Yeah, this deep dive really shows how we've moved from that fragmented world of frameworks not talking to each other to this unified standard. It feels like a really pivotal shift in how AI gets built and deployed.
It truly is. And for you, the MLOps developer, or anyone involved in putting AI into practice, ONNX stops being just another tool on the belt. It becomes a strategic asset. It genuinely streamlines that complex path from a researcher's laptop to a robust production system. It unlocks performance gains, often independent of the original framework, and gives you that incredible flexibility to target almost any hardware or environment.
So mastering these skills, we talked about converting models accurately, applying those graph optimizations, knowing when and how to use quantization, deploying effectively with ORT across different targets. This really puts you at that crucial intersection of data science understanding and solid software engineering practice. You're the one bridging the gap.
Absolutely. And looking ahead, as AI continues its rapid acceleration, think about generative AI models becoming more common. The ecosystem of tools and hardware supporting ONNX constantly growing these core principles of standardization and portability that ONNX embodies. They're only going to become more critical.
So a final thought to leave our listeners with. Think about this. What truly new, perhaps even unexpected applications become possible when any AI model, no matter how complex, can genuinely run anywhere, from the biggest cloud server down to the simplest sensor right in your pocket or your browser.
What does that mean for making AI truly accessible, truly ubiquitous, seamlessly woven into our world without being tied down by the old boundaries of specific software stacks or hardware limitations?
Something to definitely mull over.